Okay. Hi, everybody. Thanks for the help. Appreciate it. The exam is a week from Friday, right? And it's time for you guys to start working in your study groups, if you haven't been, because a key way to figure out whether you understand the material we're talking about is to actually talk about it. If you can't articulate your ideas or your understanding, it's a good sign that you don't understand the ideas. Can you guys please be quiet? Remember that I'm listening to you, so when you guys talk, I'm leaning in to try to listen to what you're saying. It's really difficult for me to talk while you guys are talking. So you also should be careful to do something in addition to coming to the lecture. I think you're at a big advantage because you do actually come, but you have to do at least one other thing. Either read the book or review the lecture again on the webcast as a strategy, because I've been talking to people in office hours, and there really are a lot of concepts that just aren't understood. And you know it, and the people I speak with know it once they start trying to articulate a concept. So you need to form your study groups and start talking about terms and concepts to determine your level of understanding. And now is the time, so you're not cramming this next week. I'm happy to try to set up office hours with you. They've pretty much filled up for Tuesdays, a couple slots next Tuesday, but we can do it outside of the regular time slots if need be. Any questions related to the exam in particular? Yes? You should understand, the question was which calculations you should be able to do. You should understand the models, you should understand the equations that you've been given, but you won't be given values to run through those equations based on your memory of the equations. The equations are important as models for helping you understand the dynamics of populations, for example, but generally you'll be given an equation if you were to work with it. Any other questions related to the exam? Any questions on anything at all? We have, how many more? The last lecture is Wednesday, right, with exam on Friday? So we have 3 more lectures after this one, ecosystem ecology today. Then we're going to form a bridge back into the past in looking at paleoecology, and we'll get a chance to look at human evolution, bringing us back up to today with a focus on contemporary ecological problems, particularly related to human health and the environment. Ecosystem ecology. We'll look at productivity at a global scale. We'll look at how you can study ecosystems on a local or landscape scale, and some examples of studies that have been done on those scales. We will very briefly look at ways to study ecosystems in terms of chemistry by following trace elements and isotopes through ecosystems. The technical background for that is not something you need to understand. You just need to understand how these things are used as proxies for ecological dynamics, how elements and isotopes are used as proxies. It's a very important field in ecology, subdiscipline within ecology now, influencing the entirety of ecology. So it's something you just have to be introduced to. But it's highly technical, and you don't need to understand the background for it. And then we'll get into global cycles, element cycles, as a bridge to understanding carbon in particular in the context of global climate change. Net primary production, we remember from last time, as being gross primary production minus what's lost in respiration. And when you look on a global scale at the productivity of different areas, different ecosystems, you see strong contrasts across the Earth's surface in productivity. Data like these are obtained from satellites, usually, based on the reflectance of light off of the Earth's surface and the interpretation of those reflectance patterns to identify how much chlorophyll is present in a particular area, and that's taken to reflect productivity. That's usually how it's done. So your scale here is net primary productivity in grams of production of biomass per meter squared per year, with your warmer temperature on this scale indicating the least productive areas and the colder blues and purples indicating the most productive. So your polar areas tend to be less productive. Your desert regions, your very dry regions, tend to show little productivity, of course. The Sahara is given as a blank here. That's certainly not true. But the point is well taken that as a great desert, as a huge desert, there's just not that much productivity relative to other systems. The most productive areas tend to be around the equator, in the tropics, and particularly the rainforests, the Amazon, the Great Congo rainforest zone, the Southeast Asian rainforests, and this archipelago here, on the terrestrial surface, right, on the land surface. What does it look like? Well, before we get into what it looks like in the oceans, let's look at the relationship between precipitation and productivity. Because we see these trends toward the equator, you might link that to some of the things you understand about climate at those latitudes. And when you look at precipitation in relation to productivity, you see increasing productivity with precipitation, but a tailing off at the extremely high values of precipitation, the very, very wet areas, a tailing off of productivity. Temperature, looked at separately, shows just a positive correlation between temperature and productivity, with the higher temperature areas being more productive. What's one major reason for increased productivity with increased temperatures and moisture? One major reason, yes. What works harder or faster? Enzymes. Enzyme action is more rapid in warm conditions where there's water available. That is true. What else? In that sense, the pace of life is quicker, and productivity tends to be higher. Yes? More sunlight available for the capture of photons in photosynthesis. That may play a role. Yes? Bacteria. Yeah, particularly in the context of decomposition. Decomposition rates are much higher in systems that are warm and wet, and that allows turnover to be faster, less material to be locked up, sequestered in living biomass, and unusable. It gets cycled through the system faster. And many of the nutrients that get cycled through the system, many of the elements that get cycled through the system are in limited supply for these systems. And when decomposition is more rapid, they become freed up and more available for the autotrophs, rather than locked up, say, in the soils. So when you look at evapotranspiration, we were introduced to that variable previously, and I mentioned that it sort of encapsulates both water and temperature within the concept of evapotranspiration. It's how much water is both evaporated and transpired from a a terrestrial surface, transpired through the leaves of plants, evaporated from the various physical surfaces, and in that way encapsulating both water and temperature. Evapotranspiration versus primary production shows differences between major biomes in their productivity in relation to how much water they shed per unit area, with your deserts or your shrublands and your tundra at the lower end and your tropical forests at the high end in the terrestrial context. In the marine context, again, your blues, no, it's reversed here. This makes more sense to me to have your cold temperatures indicate less productivity, your hot temperatures, hot just being the color temperature, I mean, the reds indicating greater productivity, shows these quote-unquote dead zones in the oceans, these very dark blues, with increased productivity, and high productivity, relatively speaking, along the coasts, right? And maybe in some of the big lakes like Baikal, it's Lake Baikal, in the coastal environments, nearshore environments. Why is productivity so high in these coastal environments? One reason is because of nutrient limitations in the marine zone. Nutrients are running off the continents from the waterways. There may be reef formation along some of these coastal areas, and coral reefs are highly productive in a marine ecosystem. But nutrients are very much limited for many of these systems. These areas are poor in critical nutrients. It may just be a single nutrient that's limiting, a single element. It may just be nitrogen limited or phosphorus limited. Many of them are nitrogen and phosphorus limited in particular. And if one of these things is limiting, it can limit the whole system. And if you add more of that nutrient, the system will become more productive until some other nutrient becomes limiting. So they can get strapped by a single nutrient. And some recent studies have shown that these areas may be more productive than we realized, these very open ocean areas. But the point is real also that these are sort of the deserts of the ocean, these zones. But the oceans occupy so much of Earth's surface by percentage. They occupy so much of the Earth's surface that even though their productivity is relatively low, the percentage of the Earth's net primary production generated by the oceans is very high because there's so much ocean. So you need to consider that when you're thinking on a global scale of productivity. Well, just how much space is occupied by the biome in question. Algal beds and coral reefs are extremely productive. They're very productive marine systems, but there's not that much of them in area. And so their global contribution may be small. The tropical rainforest, extremely productive and vast, and thus a major contributor to planet Earth's productivity. And of course, when we get into the context of environmental considerations in a socio-political context, those are important systems to think about. Coral reefs are facing major challenges to their health and survival, and tropical rainforests are being cut at extraordinary rates. They're a fraction of what they used to be, and with each passing day, their major fractions are lost again and again. So that's particularly concerning in light of their global productivity and their role in carbon sequestration, for example. So how do you actually study an ecosystem on the ground? You can do it from space, from a satellite like that, study ecosystem dynamics, but how do you do it on the ground? Well, they're usually large-scale studies. That's in the traditional idea of an ecosystem. Even though we've seen that a tree hole can be an ecosystem, your armpit can be an ecosystem, to use an interesting example maybe, as a microbiome. Ecosystems can be at any scales. They're just ecological systems. They're just interactions between organisms and the physical environment. But classically, traditionally, within this field of study, an ecosystem is something like this on a landscape scale. One of the first project areas to really get a handle on ecosystem studies, we mentioned one in a previous lecture, Silver Springs, Florida. Here's another one, Hubbard Brook Forest in New Hampshire, where in this little valley, there are these sets of sort of smaller valleys, these watersheds within this valley, 6 or 8 of them, that trap all the water that falls into them. So they have these high edges. The water that falls into them is trapped within them and either gets taken up by the organisms within it, evapotranspired out of it, or flows down it. That's the sense in which this is a watershed. It catches all the water that comes into it. The bedrock, conveniently here, the granite bedrock is impermeable, so the water doesn't percolate out of it below ground. It flows out of it if it doesn't evapotranspire out of it. And that makes it relatively controlled. So here's a case where you can study a whole ecosystem, a whole landscape, with some control because of the physical characteristics of the system in the field, and not just doing something like this in a laboratory. And what they did at these several watersheds is to build a weir at the bottom, a dam where the water was channeled, so that they could monitor water output. They could monitor how much water came out and the chemistry of the water, which reflected the outflows of the system as a whole, the outflows of the entire watershed. And so they could watch change in the ecosystem by monitoring this outflow. And you had teams and teams of investigators doing this. And they've continued to do it. So these longitudinal studies of an ecosystem over decades. It's fantastic information. These studies were foundational in our understanding of problems with regard to clear cutting of forests, with regard to acid rain. Studies from Hubbard Brook, when they were picked up by the New York Times, in showing that rainfall was becoming more acidic, lower in pH, the rainwater that falls, because of pollutants from other areas, pollutants from particularly west of this region that were getting into the atmosphere, causing the rainwater to become more acidic, which was then falling on these forests, was playing important roles in negatively influencing the organisms in these communities. The whole phenomenon of acid rain came to public attention because of the studies here. With regard to tree cutting, a typical mode of operation for a timber harvester would be to go in, and this was timber country up there, would be to go in and fell a forest and take the biomass out and wait some decades before it grew again. And these forests, they grow back pretty fast. And so the idea was, well, let's cut it. It's cheap just to go in and cut it all. It's relatively cheap and efficient, well, economically efficient, to just go in and cut everything. Leave the stuff you don't want lying on the ground, drag out the stuff you do, but cut everything. Don't go in there and pick and choose. It's easier just to cut it all. And so that was a standard practice. Well, what they were able to monitor, they actually performed these experiments. They would clear cut a whole watershed with the help of the timber groups and cut in different ways other watersheds and leave other watersheds untouched as controls and monitor differences. And in one of these experiments where they completed tree cutting in 1965, watching the watershed that was clear cut, monitoring nitrates in the runoff of the water from that clear cut watershed, a measure of how much nitrogen was being lost from the system. They showed that the nitrogen being lost from the system skyrocketed, and here's a break in the graph here, to very high levels within about a year. So the nitrate was just spilling out of the system, being lost from the system, a critical nutrient for plant growth, for organismal growth and survival. Whereas your control systems carried on with typical loss of nitrate in the system. Something similar was seen with the water itself. You clear cut the forest, and there's just much more water that rushes out of the system, as you might expect. It's not being taken up by the plants and other organisms and transpired through the plant leaves back to the atmosphere. It's just running down slope. And that helps us understand why major deforestation can impact flooding. has an impact on flooding events. And we see that all over the world, all too frequently. Major flooding events associated with the cutting of forests, upslope. You have a city with a mountain next to it that's been cut. The habitat's been completely altered. All that rainwater is flowing out in a way that it didn't used to when it would get trapped in evapotranspired or used within the system. So water followed this trend. Other elements, other nutrients followed similar trends, but nitrate, the changes in nitrate were particularly striking. And other ecosystem studies can be done in different ways. And, studies of this nature have been set up on large plots where you have a plot that's cut into compartments, and these different compartments can be treated differently and studied as little ecosystems, independent of one another, subject to the same overall weather patterns. So you assume that many of the abiotic variables that influence this plot are the same for this plot, which gives you control over that major difference, that major potential difference. Well, the climate's the same, the weather's the same for these two. So let's change one factor here and monitor the difference that you see through time. Another way to study ecosystems at this scale, or community change. Biogeochemistry is an integrative field of study integrating biology and geology and chemistry. And it's the term that's usually applied for studies of element and isotope cycling and movement within systems, within ecosystems. So these are the couple fields that I don't really need you to understand the mechanics behind it. I'm happy to talk about it outside of here. It's something that it's a big part of what I do in my research, biogeochemistry, and it's really fun and a really exciting field. And if you get into ecology, you understand this stuff because it's now standard practice. Where you used to have to spend a whole PhD just on your isotope work because it was so laborious, the techniques were difficult to master. Now you can use isotope research or trace element research as one component of your study because it's so much faster and easier to handle now here in 2012 than it was just 8 years ago. Biogeochemistry. I think one of the most famous examples of biogeochemical application came from Yosemite, here in the Sierra Nevadas, a place called Thompson Canyon. And what was followed were strontium, barium, and calcium. And you can find them on the periodic table up there if you want. And you can remember that they're all alkaline earth metals. So these are related elements in all being alkaline earths. And they exist in your tissues, in your skin, in your hair, in your bones, in your teeth. And they do for other organisms as well. They exist within their tissues. These alkaline earths do. But calcium is the one that's critical for organismal growth and survival. Strontium and barium are not essential elements, but they mimic calcium in how they function in organismal bodies because they mimic the structure of calcium. So they're taken up by organisms, but not utilized in the way that calcium is utilized and required. Organisms have a means to preferentially take up calcium relative to strontium and barium, and they preferentially excrete strontium and barium and retain calcium. So organisms biopurify calcium in their development and growth in this sense. So in this system, you have your geology, you have your bedrock from which these elements derive. They come from the eroding of the rock beneath the surface. They exist in the soil, in the humus, in the soil. They exist in the plants, for example, these sedges, and the little voles that munch the sedges, and in the martens that munch the voles. And what you can follow is the relative amount of strontium and barium to calcium in these different systems. Since calcium gets biopurified, that ratio decreases across trophic levels. So there's less of it. There's a lower ratio in the humus relative to the rock, lower in the sedges relative to the rock, lower in the voles relative to the sedges, and lower in the martens relative to the voles. Because the martens, as they eat, are preferentially excreting the strontium and barium and retaining the calcium. So see how you can go in and grab some of these things and even just take hairs off of them in the case of the mammals, or take some of this tissue, dry it out, grind it up, take it back to the lab, analyze it, look at the strontium, barium, and calcium, and start to reconstruct the food web, reconstruct trophic levels on the basis of that chemical analysis. That can be really powerful, especially when you're looking at the fossil record. Organisms that you can't watch, you can go take those fossil tissues and do the same types of chemical analysis and reconstruct the ancient ecosystems based on those chemical results. Isotopes are similarly used in ecology to the way those elements were just used in their gross quantities and ratios. Remember that isotopes exist of particular elements, and they exist in different abundances in nature, these different isotopes. Remember that your elements are distinguished based on the number of protons in the nucleus, right? So carbon has 6 protons in the nucleus, but it can vary in the number of neutrons that it has. Carbon-12 has, yes, it has 6 protons, it's carbon, but it has 6 neutrons, whereas carbon-13 has 7 neutrons, carbon-14 has 8. And neutrons are heavy. They're the same mass as protons, effectively. Whereas your electrons, which don't vary across these isotopes in their arrangement or number, effectively are massless for our purposes. Now, isotopes of carbon like 12 and 13 are stable. They don't radioactively decay. Carbon-14 radioactively decays, and that's why it's useful in radiometric dating of archaeological and fossil materials from the last 100,000 years or so. It's very useful in that regard. It's not useful in these types of isotope studies. What are useful are the 2 isotopes of carbon that are stable, that don't decay. And the ratio of the heavy one, 13, to the light one, 12, is another one of these great proxies for understanding organismal ecology. I'll just skip the details of why completely now. I know I'm losing some of you already with this, so I'm just going to skip the mechanisms behind it and just show you some results here for nitrogen, not carbon, but very similarly applied in this context. And all you need to understand is that this proxy, nitrogen values, indicates trophic level in this aquatic system and many other systems. So the ratio of heavy nitrogen to light nitrogen scales up with trophic level, secondary, tertiary, quaternary. And again, you can just measure the nitrogen in your crustacean, your small fish, and your big fish chemically and understand something about their feeding relationships. A very, very powerful approach in aquatic systems where you can just go harvest a bunch of material